Lesson 25. We're looking at section 9.7, approximating Taylor polynomials. Now, I'm going to work through 1, 2, and 3, actually 1 and 2 very quickly. I'm going to take my time with 3, I'm going to take my time with 4, because it's very important you understand what we're doing and why we're doing it. Now, with number 1 is not new information, okay? It says find the linear approximation, okay, of f of x equaling e to the x, okay, at the point 0, 1. Now, if linear approximation sounds familiar, it should. It's from Calc 1, okay? This is also referred to sometimes as the tangent line approximation, okay? And again, the idea is this. E to the x looks like this. And what I want to do is I want to, at this point 0, 1, which is right here, okay, I want to come up with a line, specifically a line, not a curve, a line that's going to approximate this function around that point. So now you'll see in red is the tangent line that I want to create. It's accurate probably about from here to what looks like to about there. Okay? Again, right in here is the tangent line that I want to create. Okay. Now, if you recall back to Calc 1, the tangent line approximation starts off with us having an equation of a basic line. Okay. This thing in particular. Well, what I can do here is, what is the slope in calculus? What is it referred to as? Well, it's always referred to as the derivative. Okay. And I want the slope at that point. Okay, at that point. So I want the derivative of the function at x sub 1. Okay, that's what that is. I'm going to have x minus x sub 1. And this is equal to y minus y sub 1. Now, I'm going to rephrase this in a certain way. Okay, I'm actually going to change all this information. I prefer f of x for y. I prefer f of x1 for y1. And this is equal to f prime of x1 times x minus x1. And therefore, my f of x, okay, is supposed to be equal to f of x1, adding this to both sides, plus f prime of x1 times the x minus x1. Okay, so now everything's in terms of x's. So I have this up here. Let me go ahead and rewrite this down here. And again, this is going to actually finish example number 1. F of x is equal to e to the x. What is f prime of x? Because I need f prime of x1. So I need to take the derivative of e to the x. E to the x in terms of derivatives, go to e to the x. Yes, I picked a really nice function for this. What is f of x1? Again, I need f of x1 for this. Well, when I plug in 0, I get e to the 0, which is just 1. What about f prime of x1? Because I need that for this piece right here. And that's, again, e to the 0, which is also 1. So plugging in all my values, I'm going to rename f of x. I'm actually going to call it p sub 1. A polynomial of first degree, okay, highest power being 1, a linear function. P sub 1 of x is supposed to be equal to, again, this is the linear approximating polynomial of, well, f of x1 is 1 plus the derivative at 1, the derivative at 0 at x sub 1 is 1. Okay, times x minus x sub 1 being 0. So this is really 1 plus x. That is the linear approximation of e to the x at the point 0, 1. Okay? This concludes example number 1. Okay? What I want to do next is I'm going to go ahead and move over here so I still have this on the same page so I can see it nice and clearly. I want to do number 2. Okay. Number 2 says, now I want a quadratic approximation of the function. A quadratic approximation of the function. I want a polynomial of degree 2. Now, why would I want this? And again, this is what I really want, and I don't even know what it's supposed to be. Well, why would I want this? I want this because if I look at the exponential function now, okay, I'm going to look at it here, same one, okay. I want to approximate it at this point, but instead of approximating it with a line, because after a certain amount of time, that becomes extremely inaccurate, okay? What if I used a quadratic? Okay, now maybe this quadratic is a little bit cockeyed. I mean, I'm not really too worried about the accuracies of the picture, but the idea is this. On this side, it's going to take us probably to about, I don't know, here, before the inaccuracy between the polynomial, the quadratic, and the original function, the exponential, is inaccurate. Now over here, it's more like right here. But then again, that distance from here to here is a lot more accuracy than we had up here. Okay, again, this down here is a lot more accuracy. Now, it might not look like it's more accuracy because of the way I drew this one versus this one, but the idea is that the accuracy here is a lot less than the accuracy here. Okay, so what we're going to do is we're going to say, well, what if I was able to create a quadratic that approximates, okay, the exponential function? It would be more accurate, and I'd be able to approximate the exponential function a lot closer using a polynomial. Okay, let's see if I can do this. Well, first of all, okay, we know that this thing here should have, well, some resemblance of the first degree approximating polynomial plus some sort of quadratic. Now, when I say quadratic, I'm going to use the same information that I had for the first degree. Okay, so this and this I'm going to go ahead and match up. Now there's something that's going to occur here. Well, since this is a slope, okay, maybe on this one I might want some sort of curvature here. Okay, maybe I might want a second derivative. There's a problem with this. There's something else that occurs. What I'm going to do is I'm going to label this as C. Okay, I'm going to label this as C, and there's going to be a good reason for that. I want this to behave in every single possible way in similarity to this. Okay, specifically at the point 0, 1. Now this is the difficult part to grasp, which is why I'm going to take my time with saying it. I need this constant value, the number that is here, because it is going to be a number. Okay, if you look back over here, the number in front of the polynomial that's a linear was a number. Yes, it's the derivative of the original function, but I plug in 0 and I get 1. I get a number. Okay, I want this value to be similar to the value of this function. Now, for me to be able to say that, what I want to say then is that P2 of 0 better be equal to f of 0. Okay, I better be able to say that the slopes at those points are the same. Again, it wouldn't make any sense for the slope of this one to go up and the slope of this one to go down. That wouldn't make any sense. I want the slopes to be accurate to each other in this section. Same with on this section over here. Okay, this, notice, is a positive slope. It's increasing slightly, going from left to right. Okay, and this one here is a negative slope, but it's getting closer and closer to this. Okay, the idea is I want the slopes at the original function and the approximating polynomial to be similar. Okay, I should probably put similar. They don't have to be perfect, but they have to be approximately equal to each other. The last piece that I want is the second derivative of the approximating polynomial to be equivalent in some way to the second derivative of the original function at that point. Okay. Now, when I make all of these assumptions, these conclusions, these statements, it means I need to find the C value such that all of this stuff is true. Okay? Well, it's easy for me to conclude this information here because this I already have. That's over here. Okay? This I don't know. Okay? But this one I do. If I take the derivatives and I plug with those and I play with those, you're going to come to find out that this thing right here, okay, this C value, and I'm not going to do the math because I think the math at the high school level is a little bit confusing, okay? Maybe in a year, if you come back to these videos and you go, how do you do that? And you ask me, I will explain it to you. But as of right now, all I want to do is I want to say that with all of these stipulations, okay, we're going to play with all this information and we're going to start plugging the values in appropriately and taking the derivatives and plugging those values in. And we're going to start playing with C to get a system of equations to solve for what the C value has to be. We will conclude that the C value is actually going to be, well, similar to this. I have a linear with a first derivative. This is going to be now a quadratic. It's going to be the second derivative at that point. But there's also an extra piece that's involved. And to make that extra piece appropriate, I actually have to divide by 2 factorial. Okay? That's what's the constant value that goes here. So, what is the quadratic approximating polynomial? It will always be, for every function, p sub 2 of x is equal to p sub 1 of x, okay, the linear approximating polynomial, plus the second derivative at that point divided by 2 factorial times x minus x1 squared. By adding that piece, okay, it will follow all of these rules. The values are the same. The slopes are similar. The curvature is similar. So the approximating polynomial should be similar to f of x, the exponential function, around that point. Okay, let's go ahead and do this math. So p sub 1, I'm going to say p sub 2 of x is actually equal to 1 plus x. That is that right there. I have it over here. I did that already. Okay. My second derivative of the function, well, I'm going to come back over here. We have our first derivative is e to the x, so my second derivative down here of x is e to the x. My second derivative of x1, because I need that, x1. I plug that in, I get e to the 0, which is 1 again. Okay, so I get plus 1 divided by 2 factorial times x minus, well, x sub 1 is 0, so 0 squared. So what is my second degree approximating polynomial? 1 plus x plus, and I'm going to leave it like this, okay, so we start seeing the pattern. X squared divided by 2 factorial, okay? That is my second degree approximating polynomial, okay? And the rule it follows is the first degree polynomial plus this extra piece, okay? I'm going to go ahead and do another video for 3 and then another video in the same light for 4 so you start recognizing the pattern.